Thank you, Marco. Appreciate the invitation to participate in the webinar and also to participate in this special issue. As Marco mentioned, my background is more in signal processing, so channel estimation is probably the most critical signal processing problem that has to be solved for these surfaces. I want to just acknowledge my colleagues here that also participated with me on this work. So let's see if I can get it to advance. There we go. So I'm going to use just a few equations, nothing too difficult to look at here. But so channel estimation really is one of the keys to unlocking the potential of these surfaces that Marco and Stefano have talked about. So I'm just looking at the RIS2 configuration, I guess, using Stefano's definitions. So in this case, there's maybe some base station controlling the surface and maybe some users that want to communicate with the base station. And let's see, there we go. And so there may be, in general, the direct path that would normally be used to communicate with the base station by these users might be blocked or very weak. And so the idea is to communicate through the surface to the base station. And so we let, for example, here G represent the wireless channels, and I'm just using this, I'm not giving any definition to these channels. This is just the name I'm giving to the channels for these wireless users. They transmit, goes through some channel G to the surface. The surface implements whatever it does to the signal. That can be a phase shift, that can be perhaps an attenuation as well. And then that signal is then propagated from the RIS to the base station. And so what you see at the base station is really the output of the individual users propagated through this composite channel that includes propagation from the users through the RIS and then back or to the base station itself. Now, if the RIS is not reconfigurable, if there is no R, I guess if it's an RIS1, in that case, the problem is not difficult. We could just estimate the channel as we normally do in any wireless configuration, and we would have no problem. The interesting part comes in the fact that we want to, for the reconfigurable case, where we want to take advantage of this environment and change this matrix phi, that's the reconfigurability, in order to tune this composite channel to have good properties. And in order for us to understand how changes in the RIS impact the channel, we have to do something more than just estimate this composite channel for a fixed phi. And that's the difficulty. Because we don't have any observations for an RIS2, we don't have any data, we don't have any observations that are available at the surface. So we cannot individually identify these three components of this composite channel. And this could be seen here by this one equation. This is the one equation that I will include in my talk here. One composite channel, F phi G, would be equivalent to another composite channel simply by introducing this matrix lambda and lambda inverse in between, if lambda is a diagonal matrix here. This just shows that we can't individually identify the elements of this channel matrix, this composite channel matrix, because we don't have any observations for an RIS2 at the surface. And so this makes the problem a little bit tricky for us in order to know how changes in the surface behavior change the composite channel. The only thing we can identify are what are called these cascaded channels. In other words, the products of the channel from the surface to the base station and the individual components of the channels from the users to the surface. So instead of being able to identify F and G by themselves, we can only identify this product, this cascaded channel. And that's what makes the channel estimation a little bit more complicated than just in a regular MIMO communication system. And one of the big, I guess, the big impact that this has is that if you don't have any information at the surface or don't have any other information available to you, it requires a rather large training overhead in order to estimate this cascaded channel. And it's on the order of the product of the number of users that you have, in this case, say K, times the number of elements in the surface, N, which could be a very large number, and hence a very large training overhead. So the question is, how do we address this when you estimate the channel? Well, the answer is in the paper. We talk about this. We talk about solving this problem in a number of ways, and we try to do it in a systematic way in the paper. We first, in the paper, discuss what we call unstructured channel models. These would be channel models where we don't have any information about the propagation environment other than it has some kind of rich scattering. We don't make any assumptions basically about these channel matrices G and F, and we try and estimate them directly without resorting to any assumptions about sparsity or any other kinds of assumptions. So we talk about least squares methods. These were the first methods that were proposed for channel estimation. These methods suffer from the problem of having a very large training overhead. We talk about alternatives such as linear minimum mean squared estimation, and some difficulties associated with using the channel covariance in these situations. We talk about not only narrowband applications, but also wideband and OFDM channel estimation. And then we discuss some methods for trying to reduce the training overhead that would normally be part of the problem. And we talk about a couple of different methods, one of them involving grouping some of the elements on the surface together to reduce the dimension of the problem, and also exploiting the fact that all of the user's signals propagate through the same channel F on their way from the users to the base station. And so you can exploit that fact to reduce the channel estimation overhead by using certain techniques that are described in the paper. So that's one part of the paper. The second part of the paper is that we focus on another way of reducing the overhead in the channel estimation by using parametric models for the channels. In other words, instead of using unstructured matrices to describe these channels, we describe them in terms of angles of arrival, angles of departure, and instead of doing least squares and LMMSE, we're going to be doing methods that use angle estimation. For example, compressive sensing based methods. And so instead of estimating the channels in an unstructured way, we're estimating their parameters. And this allows you to dramatically reduce the amount of overhead that's required to estimate the channels. But it does require that you have a model for how the antennas and the surface behave as a function of these angles, which is not necessarily easy. We talk about some decoupled approaches that save complexity. We also address the wideband and OFDM case, and we talk about reducing complexity again by exploiting this idea of having common channels, and the fact that in many cases, for example, in the propagation from the surface to the base station, the angles could be nearly stationary, and you can exploit that fact to also reduce the amount of training that's necessary to estimate the channel. And then we talk about the trade-offs between these two general classes of approach. How accurate would the estimation of the channel be? How much overhead and the training is needed? Robustness to assumptions in the model and in complexity. And we provide some numerical examples to compare these two classes. I'll just show one quick example from the paper here. This shows the mean squared error of the channel estimate as a function of the number of pilots that are used to estimate the channel. This is for a case where we have a base station with 30 antennas and a relatively small surface with only 30 elements. And the unstructured channel is shown here. Whoops, I went too far. The unstructured channel here is shown here. It has the worst performance in terms of mean squared error. The methods here correspond to methods that try to exploit the propagation, the fact that it's very sparse propagation. In this case, only 5 propagation paths between the surfaces. And in this case, only 1 user. And so you can see theoretically that there's not only is there a gain potentially to be had in terms of reducing the training overhead and estimating the channel, there's also a large gain that could be achieved theoretically in terms of the estimation here of the channel. The blue curves correspond to the Kramer-Rao bound. The red curves correspond to the actual performance that we achieve by a compressive sensing algorithm. And you notice there's a gap, and that's because of the fact that the compressive sensing uses a grid that will keep you away from the bound, but still with quite a large gain in performance compared with the unstructured approaches. Of course, some of this gain will be lost because we're assuming here a perfect model for the propagation and a perfect calibration of the arrays, but that loss should still be smaller than the gap that we see here. So there is a gain to be had by using structured channel models in situations where the propagation is relatively sparse. And then finally in the paper, we talk a little bit about some emerging topics. We talk about channel estimation with RAS 3 and 4. That's the active hybrid RAS that I mentioned here, scenarios with multiple surfaces, and also machine learning, which is becoming an important tool for channel estimation. So that's just a high-level overview of the paper. There's a lot of details in the paper, but that kind of overviews what we talk about.